I've been assured that if I just stand here and talk, you can all hear me clearly. Is this actually correct? Great, thank you, back row. So Mike Muller, in his opening keynote, and other people have also made this observation, said that where you have some sort of dichotomy of issues, there's always an opportunity for some sort of innovation. So here's one for you all. In supercomputing, as we've been hearing in the previous talk, in fact, we're always looking for opportunities to maximize the amount of parallelism, even at runtime. On the other hand, we want to be confident that the results we obtain from our exascale computations are reliably correct. Here's the dichotomy. In essence, if we run the same program non-deterministically on the same hardware, we will get potentially wildly different results. That's a problem. So there are many contributory factors to this non-determinism. The one I'm going to focus on, if you're reading the title, is floating point addition. Here's an experiment you can try at home. Take a large number of floating point numbers, I've got 16,000 of them, and add them up in different orders. If I add those single precision numbers up in a very wide position, a sort of a pseudo-quad type position, I get an answer that is computationally the same every time I add up those numbers. There is a theory out and about that gives us a prediction as to how many bits will be in error every time we do a computation. So here's running the same set of positive numbers only in 6 different orders, and we see we get a small number of bits at the bottom end of our accumulated value which are wrong, and pretty much in keeping with the theory. If I move to adding up positive and negative numbers in my lists, then the amount of error goes up rather considerably. Without wanting to spend several hours on numerical analysis, this is an area called conditioning of sets of numbers. And in essence, what's happening here is that from time to time, an addend coming in will be the opposite sign of the accumulated value so far, and the bits at the MSB all match. So all of the top few bits of our accumulated value get set to 0. This is floating point, so the whole number gets shifted leftwards so that we reobtain a number of the form 1 point something, with the net effect that all those erroneous bits at the bottom from adding up things in different orders get shifted leftwards as well. So in our simple example, I have to confess I slightly tweaked the list to make it somewhat ill-conditioned. We've got half the bits are now rubbish. If we move up to exascale type computations, it's easy to imagine that different results will be completely different from one another, and we have an unusable result. So what do people do to overcome this? This is a known problem. It's been around for many years. Well, we just use higher and higher precision. So when we're adding up lots of single precision numbers in different orders, instead of accumulating into a single precision accumulator, accumulate into a double precision accumulator. And all of those wrong bits are safely kept out of harm's way in the bottom half of the result, and the top half of our result, our single precision result, is the same every time. So we've got some confidence and some reliability back. However, we haven't actually solved the problem. We still have non-associativity of floating point summation. We've used extra power. We've used extra clock cycles. And are we not ARM? We are focused on low power and getting things right. So what does the world do when trying to add up lots and lots and lots of double precision numbers? It does this. This is called a double accumulator. We have a pair of floating point numbers, AC0 and AC1, which together constitute a pseudo-quad 100-bit wide accumulator, and that we add to that a single double precision number, Ni, and we run through this long sequence of adds and subtracts, and we end up with that number being added reliably into our double width accumulator. Mathematicians hate this because the two numbers can vary with respect to each other. The top number is always within half an LSB of the accumulated results we want. The other number wobbles around, and this situation has been called as akin to having a lovely swimming pool in your backyard without a fence. Don't let people use it, or don't let children use it at least. Excuse me a moment. So, what can we do? Well, we start with an observation, which is that the entire range of the IEEE double precision floating point number is enormous. It's almost 2,100 bits. And most people we've been talking to say, well, quad precision, 100 bits, is about okay, or maybe a little more. David Bailey made this point just 3 or 4 years ago at the Arithmetic conference. We've been talking to US labs, and they confirmed that most of their problems that they're interested in, physical simulations of interesting phenomena, let's say, they don't need more than 200 bits, if you like, double quad. Another lab said to us that most of the time we don't go below 2 to the minus 50. Well, that's most of the right-hand side of the floating point range that we have up there. So there's something not fitting here. So we want a practical, high-precision accumulator that overcomes the non-associativity of floating point addition. And ARM has recently introduced SVE, so let's put our thinking caps on and see if we can get something that's going to be of interest and useful. So our proposal is we are going to use high-precision anchored numbers, sorry chaps, not Herefordshire Pale Ale, in order to enable parallel reproducible floating point summation. So what is an HPA number? Well, it's kind of like a floating point number and kind of not like a floating point number. It comprises a wide integer. 100 bits, 200 bits, could be more if a particular application requires it. And then we have a second number, an anchor, that tells us how to interpret that long integer. Those of you with longer memories might recall block floating point was quite popular a few years back for doing FFTs and things. Well, our anchor is like a fixed exponent that we apply to our large integer. That anchor stays constant throughout a whole accumulation, so we now actually have a fixed point accumulator by definition. The thing is not floating anymore. Because the accumulation is fixed point, it is now associative and therefore parallelizable and always gives the same answers. So great. And then finally, we just say that the anchor can be set by a programmer or could be dynamically adjusted during an accumulation. So redundant long integer arithmetic, it's not feasible to build 100 and 200 bit adders. Certainly in SVE, all arithmetic is constrained to being within 64-bit lanes. So how do we build a wide accumulator inside 64-bit lanes? Well, what we do is we apply a technique known as redundancy, and if, for example, we add a few bits extra, or rather specify the top few bits of each lane are going to be used for holding carries and replicate those bits from lane to lane, then we can overcome this issue of not being able to build large adders. Here's an example. Here's a 256-bit accumulator without any overlap. If we add 8 bits of overlap between lanes, then we see we now have not a 256-bit accumulator, but a 232-bit accumulator, and the top few bits of one lane have the same significance as the bottom few bits as the next lane up. This means that we can now do, say in this example, 255 additions and let the carries build up within the 64-bit lanes, and then every 255 adds go and do something about those carries. So getting a little closer to our CPU, so our new data type has this pair of numbers, and we're proposing that in SVE we use one vector to hold the very wide number and a second vector to hold the metadata, the anchor points, the amount of overlap that we have between lanes, and so on and so forth. It now turns out that we basically need 2 instructions. So this makes our architects terribly happy because that's not a large amount of opcode space. So in principle, what happens is follows. We have, for example, if we're converting into a 4-lane HPA, we broadcast our floating point number f to 4 lanes simultaneously. These all overlap by just a few bits, as I showed in a previous slide. Each lane now grabs the bits of that floating point number relative to its position in the HPA number, and each lane knows what its position is from the metadata. Having converted our floating point number into an HPA format, now a very simple 64-bit integer add across the vector adds that HPA number into an accumulator. Here's just an example showing how a floating point number, 2 to the 56 times 1 point all ones, would end up converted into 2 HPA lanes depending on the anchor points for each of those lanes. Note that in this conversion, the top 8 bits are kept at 0, because those are reserved for when we do the accumulations. Excuse me a mo again. And we're 2/3 of the way through, chaps. So SVE, if you've not heard of it, there's lots of it going on around and about at the moment, but SVE, the Scalable Vector Extension, architects vector registers, and the vector registers on different CPUs could be different lengths. The notion being that SVE software is vector length agnostic, so that somehow a system reads the availability, the width of the available registers and self-adjusts in order to take maximal advantage of the parallelism available. This does not look good news for HPA, where we're saying, well, we want to set up a nice wide vector. What happens if that nice wide vector doesn't match the vector width on our HPA, on our SVE-enabled CPU? Well, it turns out we should actually recast HPA as an SVE problem, so that in SVE we are encouraged to think of scalar problems being replicated across a vector. So here we map our wide number across several SVE registers. So each register corresponds now to one of the lanes. And if we have very, very wide registers, then you can put lots and lots of accumulators down. If we have a very, very narrow CPU, very narrow registers, then we'll only say put down 2 of these accumulators split across a number of different registers. And this works absolutely fabulously with HPA. Because we're associative, it doesn't actually matter how wide or narrow our SVE vectors are. We're going to add everything up in some order or other. Different CPUs will add things up in different orders because they'll have different vector widths, but we will still get the same result. So just to get even more into the grits of this, so here's some floating point numbers stored in a bunch of vectors. We thought long and hard about the metadata and ended up thinking realistically the best way to do this is to store the metadata across a vector but replicate it across the vector. All other solutions seem to involve broadcasting some scalar across a vector, which mitigates really against the whole point of vector processing. We also found that the amount of metadata we need is rather less than 64 bits, so actually you could easily fit 2 lots of metadata for 2 different lanes into one 64-bit SVE element and just index between them. And our fundamental instruction there shown at the bottom is F floating point convert to HPA and add. F for float, convert for convert, and so on. This instruction has 3 registers in keeping with SVE ways of doing things, and in the hardware the logic is actually very similar to an existing instruction, convert float to signed integer. So I'm just going to run through a sequence of instructions to show how these accumulators could be built up. So here we are, we've got a bunch of metadata stored in the top vector, VM0 broadcast across the whole of the vector, sorry, not broadcast, specified across the whole vector. Our first vector of floating point numbers comes in, and we convert them using that metadata 0, VM0, into the destination register at the bottom. Now we change the index, we just rerun the instruction with the 1 bit in the opcode changed, and we accumulate those same 4 numbers into a second accumulator register. These are now our 2 lanes in every column of our accumulator. Let's grab a bunch more floating point numbers in another vector, change the index back to 0, and accumulate those guys into ZD. Now change the index, convert those same numbers again into the second destination, and keep going, and keep going, and keep going, until eventually we end up with 4 independent accumulators which have all accumulated the floating point numbers from their own columns. And we've done this in a vector length agnostic SVA style. So if the vectors were twice as wide, we could be processing 8 accumulators and getting twice as much performance as if there were 4 lanes. We do need some other operations. For example, every now and then, I've referred to this earlier, we will need to do something about the carries that are built up in the top of each lane. Well, that's quite easy. We shift those carries right back down to the LSB end of the vector and then add them up somewhere else. From time to time, we need to add up all of our HPA accumulators scattered across our lanes of our SVE vectors and add them all together, so that's a reduction, and presumably at some point we would want to convert back to floating point. So we did some performance modeling of this stuff to see where we land with regard to other techniques. So the top line shows adding up vectors worth of single precision numbers into a double precision accumulator, a vector of double precision accumulators. So this is SVE, all the lanes being done in parallel. Every loop comprises 5 instructions. We have the loop overhead itself, increment, compare, branch, and then we have a load and a floating point add. So there's the 5 instructions per vector, and that takes about 2 cycles per vector to process. We can unroll the loop so that we have two loads and 2 adds per iteration of the loop, and we get a great performance. That double-double technique I showed you earlier is massively slower. It gets you more bits, as shown in the second column there. Again, somewhat a little bit unreliable, but it's okay. The top 53 bits are pretty rock solid. A couple of years ago, Demel and Noyen from the University of California at Berkeley published a software technique for attacking this problem. They get more reliable bits, but still at a rather high performance compared to just accumulating into a simple floating point register. Our techniques, HPA, achieve pretty much the same performance as accumulating into simple double precision register, but with many more bits being reproducibly obtained. And I'm getting scowls from the front row here, so I will stop with my final slide. Thank you, everyone.
Questions? I think we have time for 1 or 2. Okay, so I'm going to ask a question about how this scales downwards towards, FP32, FP16, and B-float, which is getting, increasing interest from the machine learning community. Do you see the, balance, the efficiency equation changing in any ways?
Yes, for the better. For example, HPA is organized into 64-bit lanes with 1 lane per HPA digit. And I've just been talking about accumulating double precision numbers, if you like, 1 at a time. Now, there's no reason why my Zn vector here couldn't hold 2 single precision numbers per 64 bits or 4 half precision numbers per 64 bits. And we convert all 4 of those and add them all together into the accumulator in 1 64-bit lane. So, yes, multiple precision floating point is something that's suddenly happening on the radar. And yes, you might have seen David Bailey himself is coming to give a talk to us later this week on that topic.
One last question, if anybody has one. Okay, let's thank our speaker.